Hello and biri lang, hindi naghanging computer. Hello and welcome to another session of food physics. So today we'll be continuing on rheological properties, specifically those leading to food texture profile analysis. So come on and let's get started. Okay, let's start off by looking at the strain gauge denture tenderometer. Okay, this thing, mukha siyang something you'd find mula sa isang cartoon, no? Pero it's actually a real thing. Developed in the 1956. The name is a handful, and yes, that's how they spelled cage back then. Um, and which is the predecessor to the texture profile analysis machine that we have now. So obviously, the idea we here was gayahin kung paano ngumuya yung literal na bibig, no? And try to find out useful information about it, which eventually led to objective measurement of food texture. So obviously, this allowed the measurement of changes to food texture as a result of processing ingredients and storage. No? Like if you had a sample, ano yung magiging response nitong machine na ito 1 month after the product was produced, or if you had an ingredient substitution added more of a certain ingredient. And as you know, for example, kayo mga bakers, di ba? Alam niyo yan, if you add more sugar to your cookie, ito yung making effect niya. If you add more flour, if you add more water, and so on and so forth. So essentially, this predecessor eventually revolutionized how products are made or developed. But of course, this is not how the modern day texture profile analysis machine looks like. So the TPA that we use now, or the texture profile analysis method, and the corresponding equipment was developed over time, no? But this was started by General Foods Corporation in 1963 with a team of scientists led by Dr. Alina Sermaka. You just try to pronounce that last name for yourself, no? Apat na consonants in succession. So, bahala na kayo kung paano i-pronounce yan. And its goal was to provide objective measurements of texture parameters in relation to food acceptability. So, they had an instrument which you can see here. There is a General Foods texturometer. And the original design was a two-cycle compression test to simulate successive chewing action of the mouth. This two-cycle compression is actually still being used up to this day, of course, but with a different looking texture profile analysis machine. Then this was then adapted by Dr. Malcolm Bourne for use in the Instron Universal Testing Machine. So kung nakita niyo yung napakalaking bagay na yan, yan yung Instron noon. Yung Instron ngayon is just a desktop equipment, no? A bit big for your desk, maybe taller than a blender and with maybe 4 times the footprint, but a benchtop or desktop equipment nonetheless. So as you can see here, there are a number of different texture profile machines available. This is from one manufacturer, and then there are a lot of attachments. Kung kumita niyo yung ulo niya, yan. So dyan nangyayari yung texture profile analysis. The one advantage of this test is that it's simple to conduct. Once you prepare the sample, salpak nyo lang siya dun sa machine, press, and it will operate up and down, okay? And there's an availability of different attachments. So iba yung for paste, iba yung for different types of solids, no? So virtually kahit ano pwede mong ilagay dyan, mga mamon, ganon, medyo mas matigas na breads, chicharon, cheese. Meron siya for snapping things into two. You can use it for dry noodles, wet noodles. There are things for pulling things like, applying shear force and the like, no? However, it is a destructive test. Therefore, after you've tested the sample, well, it can still be used for some other physico-chemical tests, pero essentially, hindi mo na pwedeng mabenta yung sample na ginamit mo. And because there's a lack of standardized procedures, there's a general limitation. To say you're gonna use it for quality control, you can only use it for within your products. It's not easy to compare data apples to apples. Now, if you run the numbers, if you use slightly different methods, then you cannot compare the data apples to apples, or by the sheer nature of the test. Even if you use the same data, the meaning would be less if you used it inappropriately for the type of product that you have. But more on that later. Alright, so you may watch the video on the link on the screen, and I hope as you watch it, you realize kung gaano kalawak at gaano ka-versatile ang texture profile analysis, what it can be used for, and basically have an idea of what it looks like during testing, no? Kasi wala tayong ganito, medyo mahal na equipment ito, and pangarap namin magkaroon ng ganito sa Che. I will make it my goal to get uh, funding for a project that would need the use of this one so that we could buy one for the college. It costs pretty much as expensive as an entry-level brand new car, up to about around the ₱1,000,000 mark, no? So, pangarap pero sana magkaroon tayo. There are a few around UP naman that we could use for a fee, of course. And there's also one in the OST which I used for my thesis, again for a fee. Pero sila nag-operate. So when it comes to analyzing the texture of solid and semi-solid samples, or sometimes very viscous liquids, we do use itong pinaka most common is the TPA, or texture profile analysis. So what it does is, as you have seen in the video, so meron parang probe na bumababa, and there's a force detection na nagaganap. So, para malaman niya na hindi lang air yung natatouch niya, pero yung solid or semi-solid sample na. So, you set a trigger force, and when that force is exceeded, then, uy, ito na yung sample. Ito na yung signal na yun na pala yung sample, na touch na niya. And then, what it does is to compress the sample at a constant speed until predetermined compression is reached. So, it will record the initial height nung na-trigger yung, na-exceed yung trigger force, and then it will calculate a fraction of that height na magko-compress siya until ma-reach yung height na yon. Since the compression is done at constant speed, so to achieve this constant speed, vinavary niya yung force na ina-apply niya, yung downward force, hanggang sa ma-achieve yung constant speed na iyon. Okay? So parang ito yung unang nguya, the first chew. So let's say for 50% compression, and then the probe will go up to its original height, okay, which is the height when trigger force was exceeded at whatever the predetermined test speed was, okay. So yun naman yung parang pag after mong umaya, yung aangat uli yung bubukas uli yung bunganga mo, okay. And then there was a second compression na nagaganap. So definitely between the first and second chews, marami kang data na makukuha doon, no? Kasi yung ibang bagay, pag the brittle stuff, yung first chew mo madudurog siya. So yung second chew, wala ka nang masyadong mangunguya. For the very elastic foods, no, yung first and second chews mo definitely would have a similar texture profile, or yung pinaka-curve ng first and second chew similar. So, and anything in between, no, na values. We'll see the graphs later on to try and analyze them. So, meron second compression na magaganap following the first few steps, no? And the 2-bite process ends when after the second compression, the probe returns to its original position at a predetermined post-test speed. So that might seem like a handful, or rather a mouthful, but essentially para mo lang nilagyan yung bunganga ng 4 sensors, tapos nagnguya ka twice, no? So ito yung output ng 2-bite test at sample output nito, no? So as a function of time, you can just see the amount of force needed to proceed with the test. Okay, so
Makikita mo dito yung peak, tapos yung release. Meron pang negative force. Negative meaning, kasi di ba pag positive yung force, ibig sabihin pushing downward. Pag negative, it's pulling up. Okay, so something like nagre-require ka ng effort para buksan yung bunganga mo. Kailan ba nangyayari yun? Pag may dumidikit na stringy cheese or something, di ba? Then second bite. So definitely on the second bite, there are a lot of changes. Meaning, for example, parang lumambot na yung pagkain such that mas madali na siyang ma-pierce through, etc. So there are different values here, yung peaks, yung areas under the curve. And meron silang technical designation, yung mga A2, A1, etc., P, D. We'll look at those in a while. Again, this one is a force time plot for a 2-bite test on a cylinder of brie cheese with a diameter of specific diameter 15.7 millimeters and a height of 15.6 millimeters. So, very small to, no? Less than 1 cubic inch. Very small sample of cheese. So, if you happen to read a journal article on what do you call this, yung may mga texture profile analysis, they usually use the following terms as you can see on this left hand side, and those are actually derived from um, the graph you saw on the previous slide, no, for example. So we'll just look at this. Hardness is the force required for a predetermined deformation, which is typically yung point at peak P1 kanina dun sa previous slide. What this means, of course, is kapag mas halimbawa, ang predetermined deformation mo is 50%, this is arbitrary, no? Ikaw bahala mag-set nun unless may protocol kang sinusunod. The more force needed to deform your sample to a certain degree, then the harder it is. But of course, if you look at the type of sample, kailangan mo rin i-take into consideration kung may sense ba yung term na hardness. Like for example, you're measuring the hardness of a marshmallow, parang ganon, di ba? Versus measuring the hardness of, say, a candy, di ba? Magkaiba yun. Yung interpretation, I mean. Fracturability, force at which the first significant break in the curve happens. So, yun yung F1 sa previous slide. So definitely pag nag-fracture siya, biglang magkakaroon ng drop doon sa force. If it happens at the predetermined compression, that may not make much sense, no? Kasi pinili mo yung predetermined compression na yon. But sometimes it happens before that. Cohesiveness is the strength in internal bonds of the sample, as it is a ratio of areas 2 and area 1. Then it has no unit or dimension. Dimensionless siya. Okay, so parang between the first and second choose, yung kung paanong lumiliit or lumalaki yung area between the first and second choose. So that tells you something about how cohesive the sample is. Adhesiveness, on the other hand, is the work required to overcome the sticky forces between the sample and the probe. So that's your A3, as you can see in the previous slide. Gumminess is the energy needed to disintegrate a semi-solid food. And you can see that here, hardness times cohesiveness. And chewiness is the energy needed to chew a food until it is ready for swallowing. It is hardness times cohesiveness times springiness. So, mahirap ang i-digest sa ngayon, but if you're gonna interpret texture profile analysis results, you better take this into mind. So, I suggest you switch between this and the previous slide and try to see kung ano yung meaning nun sa graph. Lastly, we have springiness and stringiness. So, springiness, originally referred to as elasticity, is the rate at which a deformed sample returns to its original size and shape and is measured as the time d2, while stringiness is the distance traveled by the probe during the negative force area A3, which is measured as your D3 dun sa graph mo. So from the table earlier, hardness is the force at P1, which is this. And caveat muna, it's only useful if the specimen sizes are and probe travel distance are the same across the samples being compared. So syempre, if you're gonna use this to compare samples, you have to make sure they're apples to apples in their size uniformity. No? Um, as a measure of firmness, you can also use the Young's modulus in its place. And usually, hardness often happens at the point of deepest compression. So, basically, ang sinasabi nito is, if you're gonna compress it, let's say, to 50% its original size, kapag mas malaking force yung kailangan mo para makompress siya ng ganon, and then technically, mas hard siya. Okay? So, of course, this assumes that you have a compressible material, no, na parang, for example, kung tinapay yan, um, kahit na nako-compress siya, may tinapay na matigas at may tinapay na malambot, even if they're both compressible. What matters, of course, there is how much force it takes to compress it to that extent. So gumminess naman is used mainly for semi-solid foods, and it's defined as an energy, but it's expressed as a force value since A2 over A1 is dimensionless and P1 is a force value. So basically, the gummier the product is, no, parang essentially mas mataas yung hardness niya and mas mataas din yung cohesiveness niya. Okay, meaning to say you need a lot of force to chew it through, and then at the same time, yung A2 over A1 kasi, no, meaning to say mas malaki yung value ng A2 over A1 kapag mas malapit yung area under the curve ni A2 sa area under the curve ni A1, meaning to say hindi gaanong nadudurog yung food after the second bite compared to the first bite, or parang mas ganun pa rin siya kahirap nguyain as the first bite, no? So and of course when you have something that's gummy, ganun yung nafe-feel mo na parang nguya ka na ng nguya, ganun pa rin yung resistance niya. Okay. Chewiness naman is used for solid food, so you either use gumminess or chewiness, but not both at the same time. If you look at how it's measured, it's pretty much the same as gumminess, except that you use D2, which is this rate measured in as a function of time. And usually ginagamit ito as a response variable in product optimization. So kapag less chewy yung product, softer siya or mas madaling nguyain. So a chewy product is basically masakit sa ulo kainin, di ba? So, okay. The original definition for springiness is the rate at which a deformed material goes back to its undeformed condition after the deforming force is removed. So technically, it's not a rate, as what you're actually measuring is distance. Kaya lang yan nakalagay dito as parang as a function of time because constant yung speed ng pag-move ng probe mo, di ba? Meaning to say, if it took twice the amount of time to get to that position, then it's twice the distance as well kasi constant naman yung rate ng distance over time na ginagalaw ng probe. Springiness D2 is the height prior to the second bite. Kasi parang mag-move lang siya to that point hanggang sa yung force ay mag-zero out, meaning hindi na tinutulak ng sample yung probe pataas. Okay? And springiness index, on the other hand, is defined as D2 over D1, or ratio of D2 to the original height. Meaning to say, after nung unang bite mo, nag-deform siya. And kung hindi man siya bumalik sa original height niya, then you measure that ratio of the height to the original height. No? Kasi kung mas springy yan, the springiest thing you could have is something that returns to its original height upon the first chew. Right?
So stringiness, on the other hand, is defined as the stress caused by adherence to the surface of your teeth or mouth, such as in mozzarella cheese. So as you can see here, yung D3, yung force area niya is negative. As mentioned before, this means nga na instead of requiring a downward force to push, it requires a pulling force or an upward force to separate your teeth or the roof of your mouth from something sticky or stringy, as in mozzarella cheese. There have been proposals to make this into a ratio of D3 over D1 instead, since the distance is dependent on D1 or the original height of the product. And if this is to be done, then the stringiness would be a dimensionless ratio of D3 over D1. So cohesiveness is simply the sum of all areas under the curve for the first and second bites. So A1C, A1W, A2C, A2W. So mas cohesive siya kapag mas malapit itong area under the curve ng second bite sa first bite. Meaning to say, after the first bite, hindi masyadong nabawasan yung parang pinaka kunat ng sample mo. It would still take the same amount of energy to chew it through. No? So if you've seen in the previous slides, when you have a certain texture profile analysis test done to a certain sample, you need to have certain factors like what type of probe to use, yung pinakaulo na magta-touch dun sa sample. As you've seen, there are a lot, may mga flat, mayroong pabilog, mayroong parang knife edge, and so on. So there's also compression, test speed, trigger force, and if the sample dimensions are very specific. So this case is yung ginawa sa master's thesis ko, although it was conducted in the OST, the test report does have the test setting. So in this case, 12.5 millimeter diameter cylinder was used. Compression was done until 75% of the height of the sample, and the test speed was a constant 100 millimeters per minute. So kaya nga sa graph, di ba, but they're measuring distance pero tinitignan siya sa graph as nandun sa x-axis amount of time. Because if you multiply that time by the test speed, you get the distance na hinahanap, trigger force of 0.005 newtons, and variable sample dimensions. Now, in this case, the samples themselves were tested as is. And of course, hindi naman sakto yun. Like, kahit keso mangun pa yung sample mo, hindi na siya kinakat. Kung ano yung size niya, yun na yun. No? In this case, the special condition para matest siya was that the samples were placed in a semi-rigid container, in this case, an origami box made from banana leaves, no? Para ma-contain yung sample kasi affected yung test results if, for example, naglagay ka lang doon, sinalpak mo isang slice ng bigo or yung suma na tinanggal mo sa dahon. Nagde-deform yung sample dahil walang nag-hold sa sides niya, and that would make the results less useful or entirely useless, to be exact. So ito naman is an example of various TPA parameters for a collection of food. So as you can see, Um, in this case, yung 25, 50, and 75% refers to yung testing conditions at which point madedetermine yung hardness. So in this case, you can see sa wheat bread, definitely if you set a deeper compression, you're likely to get a higher hardness value. And thus, if you're comparing across all bread types, hindi pwedeng magkaiba yung compression ng dalawang sample kasi that thing won't make sense. But in this case, as you can see, the same hardness for 50 and 75% compression, meaning after 50% compression, you don't need any additional force to compress the sample further. Okay, so you can see the values here for springiness. Resilience is another derived value, although we haven't discussed this. So fracturability we've seen in definition, and it's not always applicable nga kasi bread doesn't fracture, for example, di ba? And gumminess is not applicable because hindi naman siya semi-solid food. So safe to say, yun nga, makikita nyo dito, mas mataas yung chewiness for those samples na mas matagal mo yan bago malunok, more or less. And then, as you can see here, yun, may adhesiveness sa cheddar kasi mas dumidikit siya. And if you look at the degree of difference in the magnitudes, no, you have hardness as low as 38 and as high as 53,000 no, for this range of samples. So actually, it's possible to identify to a certain degree more or less what type of sample that is based on the combination and values of the TPA parameters. No? Alright, so in this case, you can see Jello is an example of a semi-solid food. Naman sa jelly bean, if you can see here, sa 25% wala siyang fracturability. Probably because hindi siya nag-fracture at all dahil mababa lang yung penetration depth. But it does display fracturability values for 50% and greater depth. Hot dogs also did not fracture in this case. Okay, but you can see here. So sa jelly bean, sobrang tumataas yung hardness niya pagdating dun sa 75% depth. And maybe if you've eaten a jelly bean, ma-explain siya ito, ibig sabihin, mas madaling kagatin yung labas niya, pero pagdating mo dun sa bandang gitna na, or trying to bite through, mas may resistance. Okay. Same case with Jello, although sa hot dogs, apparently something like uniform yung resistance niya pagdating sa 50% to 75%. Alright, so anyway, you can just try to see these values and try to imagine how these values reflect yung actual texture, especially if you're familiar with eating these types of products. So in this case, ito yung example ng TPA for hard wheat bread. So ang sample dito ay 2 slices of very firm wheat bread with a significant yield point because the cells are initially compressed. But please take note that the second stroke has a substantially lower yield point and the second area much less than the first compression, indicating moderate cohesiveness. So after ng unang kagat, nabawasan na yung nagbago na ng konti yung structure ng wheat bread and hence mas madali na siyang nguyain, more or less. Right, so dito is a classic TPA graph for a stiff hot dog. There's a substantial fracture over here, which is definitely different from the hardness one. Okay. And then mapapansin nyo na mahaba yung buntot niya sa pagitan ng first and second bite. So ito ay measure ng springiness, no? Kasi di ba nga yung haba nitong time na ito equates to yung haba ng um, ng distance na ibinalik niya, ibig sabihin close to the original height yung binalik ng hotdog after bumitaw ng ngipin mo. Okay? And we know that to be true kasi kahit kinagat mo yung hotdog through, it still maintains its shape more or less after the first bite. So take note that many products do not exhibit the classic TPA curve, and you should not be surprised about your plots not following the ideal na itsura. So we could see a bit more of these different graphs ng iba't ibang products and have an idea of how different products look like under the TPA. So hard cheddar, on the other hand, as you can see here, um, definitely nandito yung fracture point niya. At the same time, nandito yung hardness. And it's not at the point of peak compression. So nag-fracture siya. Halimbawa, kung ito man ay 50% compression na test. Before pa mag 50%, nag-fracture na siya and doon na nag-peak yung force niya. Pero yung drop niya, plastic. No? Hindi siya yung sudden drop na almost vertical line, no? May pagka-gentle slope pa siya. Then there's a second peak during just before the end of compression. Okay. You can see also here may konting mga negative area indicating dumikit sa ngipin or something. But the relatively large differences in areas ng first and second bite means after niya mag-fracture, after ng unang nguya mo, durog na siya. Ibang-iba na yung itsura niya, no? So maybe a good exercise would be to try and use a 2-bite compression method with your mouth sa iba't ibang klaseng products. And try nyo i-imagine, ano kaya yung compression nito? Pag nag-TPA cycle, anong itsura ng graph nito? You may even try to search for graphs. So for this hard extruded product, as you can see here, ibang-iba yung itsura niya, mukha siyang jagged mountain. Okay. This product fractured many times that it was compressed, starting from around 9,250 grams, okay, at 0.385 seconds. And the TPA's single fracture value does not adequately describe the nature of the highly brittle product and its fracture mechanics. So parang multiple fracture siya dahil up and down, up and down, up and down yung labas, okay? This gives us an idea that the product is a brittle, low moisture product. Okay, most extruded products are low moisture. And of course, the fracture pattern at least followed na yung hardest point occurred at the deepest compression. So, weird pa rin, no? Hindi surprising given the brittle nature of this product that it also has no adhesion, absolutely no adhesion between strokes. So medyo weird lang itong product na to. If you can imagine a product with multiple fractures, possibly mayroon siyang multiple layers na hindi even yung structure niya as you bite through it. Maraming durog na nagaganap. So this one is a firm dough. As you can see, it is extremely adhesive. And in this case, during the first compression, the peak or the hardness did not go inside with the deepest compression. No? So iba-iba talaga yung products, and you really can see, or just looking at the TPA graph, even without maybe the values on the X and Y axis, malalaman mo na kung more or less anong klaseng product siya, no? May pagka-adhesive ba siya, may pagka-brittle ba siya, how hard is it talaga, no? So dami nating magiglean just from looking at this. So cooked pasta on the other hand, isa sa mga pinaka-notable sa kanya is the concave shape of this graph, no? This means na exponential yung amount of force na dinadagdag mo just to bring it up to a higher percentage of its um, compression cycle. So highly compressed yung product mo. No? Yung may orders of magnitude, you have 1,000 here and 10,000 there. So, kung umabot man sa punto ng buhay nyo na nagtitesis kayo and either meron na tayong TPA sa CHE or at face-to-face na or magpapa-TPA kayo sa labas like sa DOST or anywhere else, ito yung mga kailangan yung tandaan. First is that you need an appropriate probe for the application. As you can see dun sa nauna nating video, ang daming probes. Merong parang kutsilyo, merong probe na parang hinihila yung noodle, merong bilog na probe, spherical, merong cylindrical, and so on and so forth. So definitely, you want a probe that's appropriate for the intended use, no? And you want to set the same speed for compression and withdrawal so that the same distance in your graph all throughout the test. Yung kung 1 second yan, parehas yung katumbas noon na distance ng compression or withdrawal. Okay? In most cases, it's needed to experiment with multiple compression distances or percent strains to determine the optimal distance for compression. For example, kung may mga fracturable product kayo na wala ng sense na go way beyond the distance at which it fractures, then you would want a lower compression. Pero kung super highly compressible naman ang product mo na meaningful pa rin yung data niya even after 75% compression, then you could select a higher one. Okay? Although very rare na nakakita ako ng compression na 100%. No? Whenever possible, use the simplified TPA settings. No? Kasi masyadong minsan yung mga tao gusto nila, oh, I want to test this and that even if it's not applicable to my food. And then you want to use the modified cohesion. Ano na to, ng mga setting na to dun sa equipment manufacturer. No? Pero simply stated na these are the settings that are generally most useful sa mga food product. Tapos, since yung TPA parameter, these are mostly just calculated from the graph, kailangan aware ka based dun sa nature ng product mo if the TPA parameters make sense, no? So, yun nga, kaya nakita nyo dun sa mga tables kanina, merong TPA na walang fracturability. Tapos, pag nireport pareho yung dun sa cohesiveness, will you use the cohesiveness or not, no? Depende kung solid or semi-solid yung food mo. Okay? And sometimes it may be needed to have a wait time between 2 cycles depending on your test objective. And it's not always the case na kailangan mo gamitin yung TPA para sa iba't ibang textural attributes. Sometimes, kailangan mo nga ng hardness kasi yun lang yung applicable. Okay, sometimes yung springiness index yung kukunin mo, and so on. Okay, parang papansin nyo may hugot yung nagsulat nito. No? Do not conduct tests which deviate greatly from TPA methods and then call those values TPA. So, the texture profile analysis machine, although marami kang pwedeng i-tweak na settings doon, if you play with it too far, then useless na natawagin siyang TPA. Kasi hindi mo na siya ma-compare dun sa mga standard values. You're not comparing apples to apples anymore. Yun nga, as I said before, dapat alam mo, may idea ka based on TPA, alin ba dito yung mag-a-apply sa product ko at alin yung hindi. Okay, what values would make sense? Kasi kahit ma-compute yan ng TPA, pwedeng wala siyang meaningful na masabi tungkol dun sa product mo. Okay? Hangga't maaari, huwag mong i-modify yung parameters unless for your internal purposes may use siya sa'yo. Okay, and the setup should be done carefully. So in my case, since DOST yung nag-analyze ng samples ko, they actually asked for a lot of initial samples nung testing. So hindi yan yung nag-submit ako ng sample and then the next day may results na. I had to submit samples maybe 2 or 3 times kasi they had to find the right combination nga ng probes, the right sense ng mga parameters, and then they had to even recommend how my sample should be na parang itong unang sample na sinubmit mo, hindi pwede to, senseless yung data na nakukuha namin kasi pag pinush siya ng probe, nagde-deform siya, tapos kailangan mo gawa ng paraan na ma-contain siya, and thus the origami banana leaf box was born, no? Okay, use of appropriate fixtures. So may mga add-ons dyan. Hindi lang yung probe. So, kailangan nakapares din yon and for its intended use. And lastly, the compression pattern should be suitable for the food type and the subjective and target consumer. So, although the 2-byte test is standard, there are other types of tests, and of course, yung compression depth, hindi lang naman din yan puros 25, 50, and 75%. There are, you can tweak it specific to your sample, no? Kung gusto mo 33.3%, ganyan, basta um, nararapat siya dun sa properties ng sample, then why not?